Every plane you've ever flown on, the pilot can see the runway, every single one. But the Concorde? At landing speed, the nose was so long and angled so high that the pilot saw nothing but sky. No runway, no ground, nothing. They were landing a 200-ton machine at 185 miles per hour, completely blind, so engineers did something no one had ever tried before. They made the nose bend, physically move downward, like the plane was bowing its head just to see where it was going. This is the real reason the Concorde's nose bends down, and why no other aircraft in history has ever copied it. To understand why Concorde needed a bending nose, you first have to understand what made it different from every other passenger jet. Most planes fly at around 500 to 600 miles per hour. Concorde flew at 1,354 miles per hour, Mach 2.04, twice the speed of sound. At 60,000 feet, so high that if you were sitting by the window, you could see the curvature of the Earth with your own eyes. To go that fast, you need a shape that cuts through the air like a needle, a long, pointed, streamlined nose. No bumps, no curves, just a sharp, clean spike at the front, and that's exactly what Concorde had. A nose so long and so pointed that it looked more like a missile than an airliner. But here's the problem nobody saw coming. Concorde used a delta wing, a large triangular wing with no flaps. Delta wings generate lift differently. At low speeds, like during landing, the entire aircraft has to tilt nose up at a steep angle to stay in the air, much steeper than a normal plane. Now combine that steep landing angle with that long pointed nose, and the pilot's view forward is completely blocked. The available downward view from the cockpit was only about 5 degrees. That's almost nothing. You're pointing at the sky while trying to find the runway. Think about that. The fastest passenger aircraft ever built, and its pilots literally could not see where they were landing. Have you ever wondered why no modern plane looks anything like the Concorde? This visibility problem is exactly where that answer starts. So what did engineers actually do? The solution was so unusual that it has never been used on any other passenger aircraft in history. How do you land a plane when you can't see the ground? You could add cameras. You could redesign the cockpit. You could change the wing shape entirely. But this was the 1960s. No screens in cockpits, no digital displays, no synthetic vision. Engineers had to solve this with pure mechanical engineering. Their solution was extraordinary. They put a hinge on the nose. The entire front section of the aircraft, everything forward of the cockpit windshield, could physically droop downward on command. The system was designed and built by Marshall of Cambridge Engineering. It used a pair of tandem hydraulic jacks, working in parallel, each with 2 cylinders sharing a common ram. When activated, these jacks would push the nose downward around a single hinge point at the base of the pressure fuselage. The nose had 4 positions, fully up with the visor raised, used during supersonic cruise. Visor retracted but nose still up, used for short subsonic flights. Nose drooped to 5 degrees, used during takeoff and taxiing. And nose drooped to 5 degrees, the full landing position. At 12.5 degrees, the pilot could finally see the runway. With the nose drooped and the visor retracted, both pilot and co-pilot could see the ground approximately 40 feet ahead of their position. Let that sink in. Engineers in the 1960s, using slide rules and paper drawings, designed a moving nose on a supersonic aircraft. And it worked perfectly for 27 years. But would it surprise you to learn that making the nose bend was actually the easier part of the problem? Because once the nose was moving, it had to survive something that would destroy almost any other material on Earth. But the nose didn't just have to bend. It had to survive something far more extreme. At Mach 2, the air friction against the aircraft's skin generated enormous heat. The nose tip, the first point of contact with the air, reached 127 degrees Celsius. That's 261 degrees Fahrenheit. Hot enough to burn your skin instantly if you touched it. The wing leading edges hit 100 to 105 degrees Celsius. The cabin walls were warm to the touch. If you were sitting by the window, you could feel the heat radiating through the glass with your palm. And here's the part that sounds impossible. This heat caused the entire aircraft to physically expand. The 202-foot fuselage stretched by 7 to 10 inches during supersonic cruise. The plane you were sitting in was literally getting longer. Pilots had a famous ritual. At Mach 2, a visible gap opened between the flight engineer's console and the bulkhead. Pilots would slip their cap into this gap. When the plane slowed down and cooled, the metal contracted, and the cap was permanently trapped inside the aircraft structure. One BA pilot's cap is still inside Concorde G BOAG at the Museum of Flight in Seattle today. Visitors walk past it every day. Not knowing there's a time capsule sealed inside the metal, think about what that means. The nose mechanism, the hydraulic jacks, the hinge, the visor system, all had to work flawlessly while being heated to 127 degrees and then cooled back down. Every single flight, for 27 years. And there was one more part of this system that almost nobody ever talks about. Something that had to move before the nose could even begin to droop. Have you ever seen the Concorde in person, or do you wish you had? Drop it in the comments. And if you're learning something new, hit subscribe, because what comes next completely changes how you see this aircraft. Most people know about the drooping nose, but almost nobody knows about the visor. What do you think happens to the windshield of a plane traveling at 1,354 miles per hour? The glass would be hit by air molecules with enough force to heat it, crack it, and eventually destroy it. The Concorde had a retractable visor, a streamlined, heat-resistant glass shield that sat over the cockpit windshield during supersonic flight. Its job was to protect the windshield from the extreme temperatures and air pressure at Mach 2. Without the visor, the windshield glass would have been directly exposed to 127-degree air friction. Over time, it would crack, warp, or fail entirely. At 60,000 feet and Mach 2, a windshield failure isn't an inconvenience, it's a catastrophe. The visor had to retract before the nose could droop. It slid forward and down into a cavity inside the nose structure, disappearing completely. Only after the visor was safely tucked away could the nose begin its descent to 5 or 12.5 degrees. This was a choreography of moving parts at engineering tolerances that most modern aircraft still can't match. A visor retracting into a nose that's about to hinge downward on an aircraft traveling at twice the speed of sound, and it had to work every single time. Consider this. In 27 years of commercial service, the droop nose mechanism never once failed during a flight. Not once. That's engineering perfection. So we have a nose that bends, a visor that retracts, metal that expands by 10 inches, all of it working perfectly. Then why did nobody build anything like it again? So if the droop nose worked so well, perfectly in fact, why has no aircraft since ever used the same system? The answer is simple. No one needed to. The Concorde was the only commercial aircraft that combined supersonic speed with a delta wing design that required such a steep landing angle. No other passenger jet has ever flown fast enough to need that kind of streamlined nose, and no other jet has landed at such an extreme angle. Modern supersonic designs, like the ones from Boom Supersonic, use advanced computer modeling and synthetic vision systems. Pilots today can see the runway on screens. They don't need a physical nose droop. Technology solved the problem differently, but there's a deeper reason too. The droop nose added weight, complexity, and maintenance cost. Every moving part on an aircraft is a potential failure point. Airlines today would never accept a system like this when cameras and screens can do the same job for a fraction of the weight and cost. The Concorde's nose was a brilliant solution to an impossible problem, built in an era when the only option was mechanical ingenuity. It belongs to a time when engineers couldn't rely on software. They had to bend metal. The last Concorde landed on November 26, 2003. When it touched down at Filton Airfield in Bristol, the nose drooped one final time. Thousands of people lined the runway to watch. That bending nose, the one that solved an impossible visibility problem, had performed its job perfectly for 27 years. Across 2 airlines, across thousands of flights, across millions of miles. Today, 20 Concordes sit in museums around the world. And if you ever visit one, look at the nose. Look at where it hinges. Look at the visor slot. Look at the hydraulic mounting points. What you're seeing isn't just a piece of an airplane. It's proof that when engineers in the 1960s faced an impossible problem, they didn't wait for computers. They didn't wait for better technology. They bent the nose of a supersonic aircraft and made it work. The Concorde wasn't just fast. It was proof that humans could outrun the sun. And we chose to let it go. If this story surprised you, subscribe to this channel, because the next video will change how you see every plane you've ever flown on.